Thank you all very much for coming to our second workshop, Intro to TensorFlow. Before we begin, just brief reintroduction. This workshop is hosted by the Google Rowan Developer Student Club. We are a Google-backed club dedicated to solving community problems with software solutions. This is a place for you to come and foster your skills and grow with fellow developers. We host projects, workshops, speaker series, coding challenges, etc. And you'll hear more about that towards the end. We have a lot of things planned for the spring. By popular request, our second workshop is on TensorFlow, right, a machine learning library output by Google. If you're interested in getting involved in some of the club's activities, go to our website, rowandsc.com. That's made by us, maintained by us. Join our community platform provided by Google, our Discord, our Slack, though let's be honest, like no one really uses Slack. And if you have any questions, feel free to reach out to us at rowandevelopers@gmail.com. All right.
Ready. Please, God. What will you say if I told you there is an app on the market?
We're past that part. Just demo it.
Okay. Let's start with a hot dog.
Oh, shit. Yes, please. Oh, motherfucker. Jin Yang, my beautiful little Asiatic friend, I'm going to buy you the palapa of your life. We will have 12 toasts, braided palm leaves. You'll never feel exposed again.
I'm going to be rich. Fuck you, Guilfoyle.
Do pizza. Let's do pizza.
Yeah. Here's that.
Not hot dog?
If you stay with us at the end of this workshop, you will be able to build that app. All right. But seriously, why should we learn machine learning? Right. Machine learning is everywhere and everything. We use it for cancer diagnoses and World of Warcraft bots, automated power plants and cryptocurrency trading bots, self-driving cars and Tinder bots. Right. Through this presentation, we're going to go through two parts. Right. What is machine learning from a theoretical mathematical standpoint and a practical code demo? Right. We understand that the learning curve for machine learning and deep learning especially is very steep when you start out. A lot of the tutorials on the internet are sort of obtuse, hard to follow, hard to understand. Our hope is that with the provided code that we're going to provide you with, and with this presentation, you'll be able to see those tutorials and be able to get started. Not be so afraid of seeing them. Everything will look a little intuitive. So, what is machine learning, really? Machine learning is all about approximating a function based on data that we're given. In typical programming, we're given f, a function, and an input x, and we're asked to find y. In machine learning, we're given x and y, and we're asked to figure out what's the output, what's the function, f. All right, so like given some stock prices, can I find a function to predict future prices? Given video inputs from a road, can I get a steering angle? Right, given images and images that have tumors, can I find a function to map the images that have tumors? Right, or how about a really simple example? Given a set of points on a graph, can I find a line of best fit? All right, now real quick, I'm going to make a little seed for later in this presentation, something to remember, right? There's more than one type of classification, right? There's linear regression versus classification, right? Linear regression has to do with generating a numerical value, and classification has to do with sorting things into different classes. This is very different for how the architecture for our models works, and we'll get into details of that later. Deep learning is all about tuning connections between these things we call neurons. Right? So imagine a bunch of points on a graph, right, that represent something. All these are as a container for a number, right? So our first layer in a neuron, our first set of neurons is just input data, right? It comes directly from the data. All of the data, all the information stored here goes through some function and is attached by a weight to future layers that appear later on in the network. And all the future layers hold is a weighted sum of the previous layer. And so I'm gonna get into the details of this. Don't worry. But let's start with the minimal example, right? Let's say I just have two nodes on a graph linked to one node in the next layer, right? These nodes A and B have a weight between them going to node C. C contains within it some function of a weighted average of A and B. That's all it holds. Right? The values calculated through a neural network will usually normalize, though, so that we can keep everything relative. Now, what do we say when we say learning? Right? At the end of the network, the last layer of perceptrons will be the output layer. We want the outputs to be as close as possible to our known results y. We want our network to, at the end, be giving us the outputs of our data, right? Remember, we already know what our input is and what the answer should be. So how do we check the work of a neural network and tell it what to change? What configuration of weights will turn x into y? Right? So for example, here's a more complicated network. Of course, they end up more complicated, right? Let's say I pass into this x and y. So what I'm saying is I have x. I want to find a function that gives me y. So each of these nodes in this neuron, each of these neurons is holding some functions of the weights that are connected to it. Right? And at the very end here, I have a prediction y. I want to figure out how far away from what I want is this prediction. I want to figure out what did I lose, right? What's my loss? Hence the name loss function. Right? Now the loss function is just the mean error squared. So you just take y, what it's supposed to be, you subtract what you got, and you square it. This is your loss. So for example, let's say I have the line that I was talking about earlier. Right, I'm passing in the point 1, 2, and my line is y equals 2x plus 0.9. Right, I pass in 1, 2, and it gives me 0.3. So I take 2, I subtract 0.3, and I square it. That's my loss. And I'm going to keep iterating this until it gets better and better. Right? Learning is all about minimizing loss. Loss is basically how far away from the result the network is. To lower loss means to make the neural network better. How do we do that? Right, that's a pretty relatively complicated problem. We use a technique called backpropagation using gradient descent. Now these are sort of buzzwords in machine learning. These tend to scare people off, and the hope that we have is we're going to give you a very simplified view of what these techniques are actually doing, so that you can get to the code and start using these technologies in your own applications. So the idea here is I have some loss based on what my network said about my input data. And I want to use this loss to sort of turn the dials and knobs for the weights in my network. I want to change them all so that at the end I get y exactly, or very close to y. Right? If the loss is large, the adjustment should be large. Right? So let's say my loss function was something simple, like the parabola for x squared. Consider the blue line on the right. I know that this line is very steep, and I know that it's very far away from my minimum. So I know that I should nudge it a lot to the left versus my green line. This is very close to my minimum and not very steep at all. So I know I have to nudge it to very little to the right. Intuitively, you can see that there's a way to use the values of the loss function to tune our weights. This is actually called a gradient, right? But this is sort of beyond the elements of programming that we'd like to highlight. If you'd like to know more about this, we can point you to some sources, and you can always ask us. But for now, we would like to move on to a code demo. Right? So before we see that, remember, we're making predictions. We're adjusting weights using a gradient derived from a loss function, then doing that again and again until it works. Right? At this point, I'm going to hand it over to Evan, who will go through a notebook. I'll share that notebook in chat so you guys can follow along with him and run the code. And let me just put him up here.
Hey, so I'm going to go over the practical elements of what Sarosh just presented. I'm Evan Pierce, by the way. So let's get started. We're going to start out by just importing the libraries that we're going to be using. So basically, we're just going to be using TensorFlow, of course, NumPy, which is a numerical computing library, and matplotlib, which will let us plot out and see the results. So we're going to start out by making a sample data set. And what this data set is we're essentially using X, and we're going to try to predict, we're going to try to make a line that predicts this, that best fits this data. So Y right now is just, yeah, it's a line. And it's based off of X. So the ground truth equation is 2X plus 0.9. And then we're adding a little bit of noise just to create these deviations so that it's not exactly a line, but it's very close to a line. So what we're trying to do is we're trying to create a line that fits this. And if you remember from middle school and high school, the equation for a line is y equals mx plus b. So what we're going to try to do is we're going to try to tune M and B until we get a line that fits this data. So we're going to try to do that. We're defining right now what variables we'd like to tune over the course of this. So let's define those now. Creating a TensorFlow variable essentially marks these as things that we would like to change over time. So you can see that by default, the variable holds a whole bunch of information. And you're going to see .numpy getting called on a lot of different objects. And I want to point out now what this is doing. So by default, tf.variable holds a bunch of things. We just want to see this numerical component. So we're using .numpy to get this numpy component off of it. I'm defining this plot function right now so that we can see what our line is doing. So right now, M is 0.05 and B is 2. And we can see that plotted on the graph. This line sucks, but we're going to try to make it better. So we're starting, the y-intercept's 2 and the slope is 0.5. So you can see that. So this is really where we're getting to the meat of what we're doing today. And this is really the meat of all of neural networks, is getting these gradients and then using them to update the weights. So we're going to use TensorFlow gradient tape in order to record all of the calculations. So anything that's indented under this width block is going to be recorded by this tape object. So the tape is watching, it's saying, okay, I see Y prediction. How are we getting Y prediction? It's going to record that M and X and B were used to get Y prediction, and then it's going to record how it's calculating the rest of things under this function, or under this, in the scope. The reason this is important is when we ask it later to figure out how to change the losses, or how to change the weights, we have some way to go back and figure out how the calculation was performed. So we're going to start out by creating all of our predictions. So this is just predicting, given the X, what each of these Ys would be. So I'm actually going to run this because it's much easier to see when you actually see the numbers. So we're creating predictions. So our first prediction is 2. And that's because our first X value starts at 0. So by default, if the X value is 0 and we're using Y equals MX plus B, that's just going to be the Y-intercept. So you can see that it starts at 2. That's what we're predicting. And you can see the truth value is around 1.3. So we can see that down here. And essentially what these numbers are is we're comparing the predictions to the truths. And each of these are element-wise exactly the same. So this is what it predicted. The second element here is what it predicted for the truth. So next, let's calculate the loss, because now we have all our predictions. So the loss is going to be the squared error. So we're figuring out how far away are we from actually getting this answer right, and then we're squaring it. The reason we're squaring it is that it makes all of the, it has two effects. We're making all of the values positive, and we're making all of the values that are more wrong be penalized more, exponentially more. So we can see the effects of that right here. For the first example, we have this amount of loss. For the second example, we have this amount of loss. But we want one number where we can say this is how well the network is doing. So what we're going to do is we're going to sum up all of those loss values. And that's what we get. But what if we add 5 more examples to this? We don't really want our loss to just grow and grow based on the number of examples. So we're just taking the average right here. And that's how we get our loss function, which is mean square error. And it's called mean square error because we're taking the error, we're squaring it, and then we are taking the mean. So if you were wondering why it's called that, that is why. So after we're done these calculations, we can use gradient tape to figure out the gradients of each of these weights. So I'm going to run that. And what this essentially allows us to say is, I have my loss, and this loss is this number right here. And how do I change M to make this number smaller? That's what the gradient is telling us. It's actually telling us how to make this number bigger, but it's a little detail. So this is the gradient for our M, and this is the gradient for our B. And what we want to do is we want to use these gradients to figure out how to change the weights so that we get a lower loss next time. And the lower loss signifies that we're getting a better fitting line. So we're going to go into how to actually update these weights now. These gradients are very large relative to the things that they're updating. So we only want to take a small portion of them. So what we're doing is we're saying for that variable M that we defined before, we want to subtract off a portion, the learning rate portion of the gradient. The reason you have to use a signed sub here is because a variable object specifically needs you to call a signed sub. But this is essentially the same thing as saying M minus equals, or M equals M minus, and then the same thing here, but just doing it with TensorFlow variables. So if I do that, we can see the new weights. So M started, if we go back up, M started at 0.05 and bias started at, or the y-intercept started at 2. So we can check. So it went up, the y-intercept, and the slope went up a lot. So if we go up here again and we calculate, the loss was 3. Now it's 1. So technically this is a lot better than what we had before. And then what we can do is we can calculate the gradients again. And notice how the gradients shrank because we're getting closer to a perfect network. So we shouldn't be changing the weights as much because we're closer. And then we can update the weights and you'll see this line become better. So this would be really boring to sit here and go through these 3 functions. So what we did is we just put all of those lines of code into a function called TrainStep. So we're going to define that. And then what we're going to do is we're going to run this epochs amount of time. An epoch is something that you'll hear a lot in machine learning. It's essentially one iteration over the entire data set. Because our data set is just these points, we can fit them all into memory at the same time. So one epoch would just be one train step in this case. So if I run this, we're running 80 epochs, and you'll see over time that our line and our loss continuously goes down until we have a line that fits extremely well. So that right there is the essence of machine learning. That's basically, from there, everything just builds on top of those core concepts of calculating gradients and updating weights with them to figure out some function. So now we're going to look at a lot of this code is going to be the same across every model that you write. So what TensorFlow has done is created a library called Keras, which builds on top of these concepts. So it creates further abstractions on top of this so that you don't have to write that out every single time. So Keras is a high-level library built on top of TensorFlow that makes things easier. What we're going to do is we're going to write the same thing, but using Keras. And we're going to see how few lines of code you actually need to do the same thing, but in Keras. So we're starting out by creating a subclass of Keras model. The reason we're doing this is because Keras.model comes with a lot of base functionality. And then what we're doing is we're just changing the little bits that we want to change to make it unique to our model. So we're going to start out by creating the same exact variables. And then we're going to define this call function, which essentially tells Keras, what do we want to do when we're actually using our model? And remember, a model is just an arbitrary function. So in this case, we're using M, and then inputs is our X plus B, and then we're returning it. So let's regenerate the data, or I'll make that class, and I'll regenerate the data. And we're making the data is exactly the same. We're creating an instance of this model, and then we're calling model.compile. Model.compile is where we choose our loss and our optimizer. So remember how before I was saying we were using mean squared error. Look, it shows up right here. We're using mean squared error. So what this is doing is exactly the same. If I scroll up, it is this portion of our code right here. That is mean squared error. The model that we defined, that is this portion of our code right here. And then the last part you'll see is optimizer. So we have stochastic gradient descent. You can ignore stochastic for now. Just know that this is gradient descent. So in our manual loop that we wrote, we have gradient descent right here. We are calculating the gradients and then using that to update the weights. And then finally, we have one more function here. We have model.fit. And then we have a number of epochs. So as you can guess, we also just wrote that from scratch. We said for I in range epochs, and then we're calling TrainStep. So that is, we have essentially written the model, the loss, the optimizer, and then the fit loop. But Keras allows us to abstract away a lot of those details and then just create the same thing in much less lines of code. And it's much easier to reason about things when you're creating these higher level abstractions. So this already has trained. You can see the loss is relatively low. I'm actually going to turn up the number of epochs just a bit higher because it doesn't take that long to train. And you'll see that the loss gets very low, very quick. And then what we can see is we can print that out and we can see the line that it just trained. So this is great, but who cares about linear regression? Let's go and do something that's a little bit more interesting. Let's try to predict the hello world of machine learning applications, the MNIST dataset. The MNIST dataset is handwritten digits. I'm not sure why it's called MNIST, but it's just a bunch of numbers. So I can refresh this and you can see different pictures that are coming out of this. The way that pictures are represented to neural networks is as a collection of pixel values. So in this case, we have a 28 by 28 image. And each one of these squares is a value between 0 and 255. And that represents how on or off the pixel is. So what we're doing in this neural network is we are just squishing that down into 784 pixels. So in this case, 784 comes from the fact that when we squish down a 2828 image into one long vector is 784. So in this case, we're still using y equals mx plus b, but in this case, we're creating a variable for each one of the pixel values. So we're creating 784 weights for each of the pixels. So each pixel has an accorded a weight associated with it. And then we're going to use that to try to predict which number this is. So I'm going to run this. And you will see this is actually doing really badly. And this is kind of expected. We're trying to perform regression, but we're actually trying to do a classification task. So that seed that Sarosh planted in the theory, if we scroll up and we look at it, one second. Here we go. We're actually trying to discriminate between class 1 and class 2. In this case, we have a bunch of numbers. We have a bunch of digits. What we were trying to do before was predict on a sliding scale the value. But right now, we're just trying to predict, is it 1 or 2? So we need to change our problem a little bit. And you can see that this is not getting any better over time. So how do we actually make this better? So what we're going to do is we're going to do two things. We're going to make our model a little bit more advanced, and we're going to change what we're trying to predict. So we're now using a multi-layer perceptron model. This is comprised of a few different layers, and we're now we're making the jump from y equals mx plus b, and now we're moving to actual Keras layers. So these layers are abstractions that are just layers are essentially functions, common sets of functions that people will use. So dense is essentially y equals mx plus b, but 32 times. So it's the same thing. You can see actually from the documentation, I ripped this right out of it, is that we're essentially taking the inputs, we're multiplying it by the weights, and then we're adding a bias, which is mx plus b, exactly like before. This 32 just means that we're doing it 32 times. So each of these linear regression classifiers is going to output their own weight. And this allows each classifier to focus on a different aspect of the image instead of only being able to focus on one thing at a time. Then we have 32. We've now translated this image from pixel values to 32 random features. And now we're passing that to a prediction layer. And this prediction layer has 10 nodes in it, or 10 classifiers. Each of those classifiers is responsible for answering the question, how confident am I that this is what I'm trying to predict? So the first node, maybe this will be easier if I go to Paint. There are 10 nodes in this final layer. Essentially, what each one of these nodes is trying to do is say, I'm this confident that it's a 0. I'm this confident that it's a 1. I'm this confident that it's 3, and so on. So each of these is going to output a value. So I think I'm 50% confident that it's a 0, and then so on. And then maybe this will be 25%. And essentially, when we're looking to figure out whether or not the model was correct, we're just going to take the one that has the highest percentage confidence. This softmax function on the end, real quick, is all that's doing is it's guaranteeing that these probabilities will add up to 1. So if we just kept adding up all the probabilities for all of the different nodes, that would add up to 1. And that allows us to just take the highest probability, which is really nice. It makes calculating things like accuracy very simple. So we can run this, and we'll see that we have much better results. We're also using a different loss function here because we're comparing probabilities now and not regression. This is something that we've chosen to kind of gloss over how this internally works, but just know that cross entropy is what's used for classification tasks, not mean squared error. but we can still use the same optimizer. And now I've included this accuracy metric that allows us to see during fit the model that's coming out. So we can see, just looking at the questions real quick. Is the confidence linear when you go down, or could it be that 2 is more confident? I'm not sure what you mean. Is confidence linear when you go down, or it could be 2?
So I think what he's asking is, does the confidence in each output layer scale linearly with each epoch? I think that's what he's trying to get at. Like, will it happen in linear time? Is that something like that? Is that somewhat correct? Abdullah.
There might be a little bit of delay.
Yeah, there probably is a little bit of delay, but if that is the case, here's what we can sort of say to that. If the database, if the data is really good and very obvious and has a very well-defined pattern, then after just one update using the gradient, you'll see like exponential improvements. But you're going to have diminishing returns on those improvements the more you iterate. So generally, it's not linear. Generally, you can expect it to be really good at first, and then it's going to start leveling off until at some point, diminishing returns, you're no longer going to be incentivized to keep using computing power, right? Does that answer your question?
I think also another thing to point out is that the network is going to train exponentially slower over time. So you can see that a majority of the learning was done after the first epoch. And then as we go further into these epochs, it's learning less and less over time. Something that I don't think I pointed out also is that we now have 2 data sets. We have one that we're training the data, or we're training the network on, and then one that we're testing the network on. So that's the difference between accuracy and validation accuracy, is that the network has never seen these examples before. And the reason that that's important to reserve some of your data for validating your model is because you don't want your model to memorize the examples that it's seen. You want it to generalize to things that it hasn't seen before, because that's the whole point of training this. And in this case, we're actually doing a very good job of generalizing to unseen examples. It's only very slightly worse than the examples that it's trained on, which is amazing to see.
And something else too, right? You want to keep in mind, these utilities are useful for things that we don't already know about, right? And so you can plant a seed here. You can mention, okay, what if my data set isn't very predictive about the things that I'm trying to learn about, right? What if there aren't as many clear patterns? That is why you often hear that machine learning requires a lot of data, right? You need to have a lot of, in some sense, every data point is making a statement about the problem space, right? And so you want to have as many statements as possible to fully encapsulate the problem. Anyway, I'll leave it to Evan.
Yeah, so that was great. I think that was a useful add. I think now what we're going to do is we're going to move into making this network a little bit better. So we're at 96% right now, and maybe this would go up higher if we trained it for longer, but I want to introduce a new concept that we're going to use for our hot dog classifier. And that is a convolutional neural network. Actually, real quick, are there any other questions that anyone would like to ask about what we've covered so far? Because we've gone over a lot in a very short amount of time. So if anyone is confused, let me know. And I'll give a couple seconds for to let the delay come in. And if you have any questions, just put them in chat. And if I move on, and I'll come back and I'll answer the question if I see it. Or Sarosh, you can let me know. So what we're doing here is we're creating the same exact model that we did before, but we're adding one new type of layer to it, a convolutional two-dimensional layer. So what is this convolutional layer? Why are we using it? What do these mean? We're going to go over that in a second. So I just want to point out that this is exactly the same after the convolutional layer. You've got dense one and predictions. And we're still trying to predict numbers. We're just trying to create a better neural network that predicts that. So let's go over what a convolutional model or convolutional layer does. Imagine that you have an image of a 3. So what we were doing before is that we were essentially unrolling each of these pixels sequentially into one long string of numbers. So we were saying the pixel value at this place was like 100, and then so on and so on. But we've actually destroyed a lot of information about this image because these pixels, we're destroying all of the information about where they're actually placed relative to each other. So we want some sort of function that respects the configuration of all the pixels. And that's what a convolutional layer does. Is that essentially what we're doing is we're defining filters that scan for features in this image. So how does it scan and what is exactly a feature? A feature could be something as simple as a horizontal line. So it is using this filter and it's asking the question, is there a horizontal line here? 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 And it's essentially using this method of scanning with a filter to create a feature vector. And what that feature vector is, all it is a list of numbers. So we can essentially say, if we're scanning, and we have our filter over here, is there a horizontal line here? And what we can say is, no, there was no horizontal line there. So we're gonna just put 0. We're gonna put a 0 in our list of numbers. And then what we can do is we can take this and we can just move it a little bit. And then we can do the same thing until we have eventually a list of numbers about where the horizontal lines are. So you can see there's kind of 2 horizontal lines in this. So that might look something like that. So we're showing where all the horizontal lines are in this image. And the thing is, we have many, many, many of these filters that are all extracting different portions of this image. You're probably wondering, how do we know to set this filter to a horizontal line? And that's what we're using gradients for. We're allowing the filters to automatically determine what they're supposed to be looking for by using backpropagation. So at first, these filters are completely random. So that kind of explains convolutional networks. It's not all of the math, but I think it's enough to conceptually grasp what's going on. So now we can kind of take a look at the parameters that we put in here. This 32 represents the amount of filters that we're putting in. And this 3 right here represents the size of the filter in squares. So this filter, we have 32 3x3 filters. So if we wanted to visualize that just a little bit, we have a 3x3 filter. And what that means is essentially it's a filter, like kind of a tic-tac-toe word. And if this filter was trying to represent a horizontal line like this, that filter might look something like 1, 1, 1, and then it's not looking for anything in the other parts of the filter. So this is kind of what you can think is kind of a representation of a filter, and how we're getting these values. So it's just multiplying each of the pixel values with the values in this filter that's underneath. And then we have 32 of these filters that are all scanning simultaneously over this image. So that's extracting the features out of the picture. We no longer have to flatten the picture. But then at the end, we want to flatten all the convolutional features into one array. But at this point, they've already been normalized for location. So you don't have to worry about that flattening that I was talking about before. And then we're using the same network, but instead of predicting directly on those pixel values, we're predicting on features that the convolutional layer has extracted. So let's see how that does. So we ended at 96% accuracy here. This might not actually be like a complete one-to-one comparison because it could take a little bit longer to train. Actually, we're already getting much higher. So take a look at that. The validation accuracy is really what matters when you're comparing these models. And we're already at 98% after 4 epochs. So this is doing a much better job at recognizing images already. Did you want to add something, Sarosh?
At this point, right, I want to point something out here. MNIST is the hello world of deep learning, right? And we've already made improvements to that. You know, things that are, if a classifier is already accurate, it's exponentially harder to make it better. And we're already seeing improvement. So at this point, you should be asking yourself, what else could I do to a neural network to make it even better than that? Can I mess with how the neurons are connected? Can I do a little, are there any tricks that I can employ? If you have any ideas, hold on to them, right, and come to part 2.
Yeah. So part 2 is where we're going to kind of go more in depth and how to actually, get your hands dirty with some of this stuff and trying to improve on what's already there. Because you'll find a lot of the time what happens is, I know when I was starting out, I would look at a tutorial, I go, wow, these are a lot of words. I have no idea what they mean. And then as soon as I would try to change one tiny little bit of that project, it would explode in my face. And that was not very inviting. So we're trying to give you the theoretical backing to make those changes so that you can do something new and not just have to follow a tutorial. So this kind of covers the basics. What we're going to do now is go over to, we're going to have a little bit of time for questions, and then we're going to go over to what you came here for, which is figuring out how to tell if something's a hot dog or not. Because we need computers to do that. So I'll leave like a minute, I guess. Or if I should just continue.
Right, again, our objective here is that you can take the notebook that we've made. Right, this is prepackaged extensible code. Right, the idea here is you can just take this and armed with this information, go and figure out, can we figure out if something is hot dog or legs? Okay, Evan, you work on hot dog or not hot dog. Let me get some pictures of legs and we'll find out.
Okay. So do you want me to start then, Sarosh?
Give it like 20 more seconds.
Okay.
Right.
Let me know when I should start.
You can start now. Come to part 2 to find out if we can build a model that can tell hot dogs or legs.
Okay. All right. So we're going to start out by taking a look at our data set. So to make this notebook usable by you at home, what I've done is I've hosted all of these images inside of zip. And what this block of code does at the top is that it downloads the zip and then it unzips them. So let's run that and let's take a look at the data. So let me refresh here. So if I go into this dataset folder, we have 2 classes. We have hot dog and not hot dog. So let's take a look at what a hot dog looks like. That's our hot dog photos, and not hot dog, which is not hot dog. All right, cool. We have our dataset. Let's do some imports. So we have our variables. These are just some constants that we can tweak. These were set almost arbitrarily. It doesn't really matter what you choose. It just matters that you choose something and then you can tune it over time. These are commonly referred to as hyperparameters. So the first thing that we're setting is the validation split, which is how much of this data set we're reserving to test on to see how well we're generalizing. The image size is what we're actually reshaping the images to be. So we want all of the images to be the same size before we put them in the neural network. And Keras helps us do that. So we just got to tell it we want the images to be that size. The batch size is how many images we're feeding into the network to train at once. So the stochastic part of gradient descent for stochastic gradient descent is that you can't, most of the time, you can't fit in your entire data set into one pass of, or one run of your neural network. So you have to split up your data set into batches. And it turns out that running through just a portion in batches of your data set at a time actually is faster. And it's much faster to train on these batches because it's much more efficient instead of the entire data set. And then the epoch is when we go through the entire data set. So one epoch would be the neural network has seen enough batches that it means that it's seen all of these images in the data set. So I'm going to use TensorFlow data, which is a really strong data preprocessing API. I heavily recommend it if you're ever going into trying to make your own data set or your own data preprocessing. Oh, I have to run this line. Here we go. So what this is essentially doing is this is a high-level function by Keras. So it's doing a lot of things right now. And it is pulling in all of the hot dog images and not hot dog images. And it's inferring the label of the image based on the folder name. So it knows that we have 2 classes, hot dog and not hot dog. And then we're pulling out the class names from that. And then we're doing a little bit of pipelining here. So cache, What that means is that after the image has been loaded once, it's actually going to keep it in memory instead of leaving it on disk. Shuffle is going to make it so that these images come out in a random order. Prefetch is going to make it so that these images are being loaded off disk while we're training, instead of waiting for the gradient updates to occur and then fetching off disk. They're going to both happen at the same time asynchronously. So I'm just making that data set. I'm making a training data set and a validation data set. So we can take a look at what this data set looks like and the labels for each of those. I promise this was working like 5 seconds ago. Here we go. Maybe I got a bad image. So you can see we have labels, hot dogs, not hot dogs. So let's see if we can try to fit this. So I actually adapted this model from a different project that was mentioned earlier on, but neural networks are so general purpose that it doesn't really matter. In fact, it works great regardless of what application it's on. So this data set is actually relatively small in terms of machine learning. It's only 250 images, and we can see right here that it only found 500 files, which is 250 for each class. And each class would be hot dog or not hot dog. So that's actually not very much data. So it's going to be very hard for the network to generalize across these two. There's a lot of different things that are occurring in each of these images. So we can kind of fake more data for the neural network by applying random transformations to the image. So in this case, what we're doing is we're going to randomly flip the image. We're going to randomly rotate it. We're going to randomly zoom in on it. We're going to randomly change the contrast, and we're going to randomly translate this image. So what that allows us to do is essentially create new examples, even though we're highly limited by the amount of pictures we have. So typically, the second trick that we're going to go over is typically other people have spent millions of dollars figuring out what the most efficient configuration of CNN layers is. So in this case, I'm taking a convolutional neural network named EfficientNet, and I'm just going to use that to extract features from the image. And I'm not going to train this portion of the network at all. So I'm not going to update the weights using the gradients here. And I can do that by just saying it's not trainable. The reason for this is because it is very expensive to calculate the gradients in terms of computing them. So we're just not going to do that because it would take forever. You technically could, however, I am not. I'm using pre-trained weights. So this CNN has already been trained on a different data set. And you think, okay, well, it's been trained on a different data set. How would it be useful here? It still learns a lot of useful things about images. So learning about horizontal lines is a pretty general thing. And we can benefit from that here. But that's kind of the general intuition for using pre-trained weights. So we're using the CNN to extract the features out of the image. And then what we're doing is we're creating a multi-layer perceptron, just like before, but it's a little bit more advanced because we have a little bit more advanced data. We're using 256 linear regression classifier units instead of 32 like before. We're using batch normalization. Essentially what this does is after a value comes out of the linear regression classifier, it can be a wide range of values. So it can be anywhere from -1 million to a +1 million. I mean, it can be whatever number. Normalization, all that's doing is it's making it so that those values are very close to 0 and that they don't deviate too much from 0. And that kind of balances things out throughout the network and keeps everything on the same scale. And then the last layer we have is the prediction layer, and those just have 2 units. So that's 1 for each class. So each unit here is predicting a different class. 1 for hot dog, 1 for not hot dog. The call method is just pipelining through all that, pipelining the data through the network. So we have our inputs, and then we're using the function that EfficientNet was trained on. So this is what the researchers, when they were creating EfficientNet, used to preprocess the input. We're just doing that so that we're making use of these pre-trained weights. And then we're using the random transformations. Then we're feeding it through the CNN, and then we're feeding it through our classifier. And then we're returning a result. So all we have to do to create the model I have to run the code, is create the model. And I'm compiling it. I'm using the same loss function, which is sparse chaotic oracle cross entropy, because it's a classification task. And I'm using Atom, which is it's essentially the same thing as gradient descent, but with a few extra things. This is just it doesn't really matter in terms of understanding what this code does. It's very similar to gradient descent. So that model has built. There's a couple extra things. There's one extra thing here. There's this thing called TensorBoard. So before, what we were doing is we were just looking at this text log, but there are much nicer ways to visualize this information and how the network's doing over time. So we're going to use TensorBoard. So I can start up TensorBoard by using this magic here. And what it's waiting for is for training to start, and it's going to visualize our training session. So I can go down here to model.fit, and I'm putting in the train data set. And then I'm using this callback called TensorBoard callback, and that's just going to feed training data into this TensorBoard right here. So let me just make sure that this is running on a GPU. Okay, it is. Because this model is much, much, much larger than anything we were doing here. So it will take a lot longer. And that's even with training turned off on that CNN that we were importing. So you can see it kind of freezes at 8 out of 8, and that's just because it's evaluating itself on the validation data set. So we should be able to refresh TensorBoard at this point, and we'll be able to see. I'm going to turn off smoothing. We'll be able to see how our accuracy and how our loss is changing over time. So let me refresh this again so we get more data points. So you can see, I can kind of rescale this too. And you can see at the very beginning, we had a high loss, and then over time, this loss is going down. The orange line is the training, and the blue line is the validation. So what we ideally want to see is a very low validation loss and a very high validation accuracy, because that's how we know we're doing well. So the train's always going to be a bit better because that's the data it's actually looking at. One of the other things that TensorBoard has, which is kind of nice while we're waiting for this to train, is that we can see what this this graph representation that we were showing you is very similar to how TensorFlow internally represents these networks. And we can see what that looks like by going to the Graphs tab of TensorBoard. So it is going to take a second. Let's see. Okay, we're actually done training. We got up to 90% accuracy. We actually went down a little bit. And this is just because it's starting to memorize the examples instead of generalizing to them. But this is still close enough. I mean, it's 90%. It's okay. We'll come back to this graphs. I'm not sure if this will load or if it's way too large to load in this environment. So let's see how well this is actually doing now. So we have another data set called dataset test. And these are images that it hasn't even seen in the validation set. So these are fresh images, and we're going to see how well it does on them. So we're going to load this into the test data set, and then we're going to plot out the predictions. So what this is doing is using model.predict on the images that are coming from this data set. This may take a second just because the model is very large. And hopefully TensorBoard is not crashing this just because it seems to be stuck loading. This would be a good time for questions just because I'm not sure. I think TensorBoard is probably stuck. So I'm going to see if I can cancel this. But if anyone has a question, now would be a good time to ask. Okay, I'm going to try rerunning this now. Here we go.
There should be a way to make the font bigger. Some people are asking about that in chat.
Let me see if there's a, I mean, I can just zoom in on Chrome. I think that works okay.
All right, yeah, cool.
But you can see what it's predicted and the ground truth. So we can see that our network's actually doing pretty good. For this picture, it predicted that it was a hot dog, and it is a hot dog. Prediction, hot dog. This was the value that came out. So if we go back to our picture, for this node, it predicted that it was that confident. So for the hot dog node, the hot dog node said, I'm 95% confident this is a hot dog. And you can see that we pretty much got everything right, which is really nice. So that kind of concludes the code portion of this. All these resources are available for you to play with and hack around with and see if you can and make it better or change something. So do you want to take over and wrap up?
Yeah, sure. So all this code we provided everybody the RSVP to this workshop. We're also going to put it in Twitch one more time. We're going to send it to Discord. We're going to send the slides and everything else as well. Our hope is for you to take all this code and just play with it yourself. See if you can make it better, see if it can behave differently, mess with the parameters, see what happens, and come to part 2 and see how a lot of researchers have done the same thing and come up with some new and more sophisticated techniques. Now, other than that, we will be doing some more events in the spring. As I keep saying, developer student clubs are project-based clubs. We're going to be doing something of a second info session / project update in the beginning of spring, showcasing the work that we've done up until this point. Shortly after that, we're going to be having part 2 of this workshop. And after that, we're going to be launching into web development, right, with Dart and React. Not Dart and React, my bad. React and JavaScript. But after that, we may do Dart and Flutter for app development. This workshop may also get a third part, depending on interest and depending on topics that we want to cover. Both of us have worked extensively with deep learning in the past for our own applications and went through like that arduous learning curve in the beginning. And so we're really interested in sort of seeing if we can compact that down into more usable prepackaged code segments and make it more widely available. Let us know if you have interest, and we hope to see you at future events. Thanks for coming.
See you guys.